today we'll talk about symmetry, and if I will omit the proofs, like I will be writing some statements. The proofs are available on my YouTube channel. It's kind of a little bit boring, especially for the younger ones. So I think what matters the most is to be able to apply them in solving counting problems. And yeah, so you already know where the stuff is. So the proofs of the statements that I'm going to make. All right, so having said that, so let's start with, I started drawing several shapes, and then I realized there are so many shapes in nature. I mean, we can stay here all day long. You can just come up with a whole book or even volumes of books, just different shapes, and then talking about the symmetries for those shapes. So let's begin with the circle. Can you guys tell me what are the symmetries of the circle? I think most of us, we would consider a circle to be very symmetric shape. What do we mean when we say something is symmetric? Yes, awesome. So there's already a couple of very good ideas. Yes. Okay, yes. So some of you guys are telling me to locate the center of the circle, which I did. And then you guys are suggesting draw any line through the center of that circle, any line, and you can just reflect the shape across this line. And what happens is the circle is mapped back to itself. Do you guys see that? It's as if nothing happened to the circle. If I just go ahead and reflect across that red line, a 180-degree reflection, you can call it a flipping. Once I flip it, that's it. So I get back the circle. That's pretty good. Is that the only type of symmetry involved in a circle? And obviously there are infinitely many of these. There are infinitely many reflections. Yes, there's also rotational symmetry. That's correct. How many rotational symmetries does a circle have? Yes, it seems there are infinitely many rotational symmetries as well, right? You can rotate it any angle and boom, so it's back to the shape itself. So as such, the circle has infinitely many reflectional symmetry because you can choose the axis of symmetry anywhere you want. So you can make it horizontal, any angle you want, whatever angle you want, you reflect it, it's back to the circle. So infinitely many flips or reflections, infinitely many rotations, whatever angle you want between 0 degrees and 360 degrees. And so you are back to the same shape. So that's the most pure, the most symmetric shape you can imagine in the 2-dimension. Well, actually, hold on. Well, you can imagine the point maybe. The point is a circle with radius 0 circle, right? So, and besides, it's 1-dimensional shape. So this one is a 2-dimension. So let's start with 2-dimensional objects first, and then we can go to 3-dimensional objects. And you guys are suggesting that circle has a very special symmetries, including, okay, so you can do a lot of good stuff with a circle, basically. Yes, like inversion. Okay, so let's not go into those areas for now. All right, so next is an equilateral triangle, right? So let's start talking about the symmetries of an equilateral triangle. As you can see, the way I'm using the word symmetry is very vague, right? So somehow, like it's not very formal, which I think it's good because for our audience today. Yes, let's just focus, because we are in the 2-dimensional plane, let's just focus on the rotations and reflections. What type of actions, symmetry actions, will leave the object appear unchanged? So you want to make the object look exactly like it was before you applied the whatever symmetry action that you're applying. And yes, so again, we can think of rotations. For instance, if I apply a 60-degree rotation, let's say clockwise rotation or counterclockwise, doesn't matter, you will get a shape like that. No, you change the shape, right? Applying a 60-degree rotation won't do it. So we need another rotation, right? So the rotations, yes. So you need a 120-degree rotation 240-degree rotation, or 360-degree rotation. In general, you can rotate any object 360 degrees and you're back to where you started. So this is usually called as the identity. All right, so this is always a rotation. Identity is always a rotation. But then a lot of you guys are suggesting in the chat box that, hey, we could have also used reflections. Yes, there are also 3 reflections. Namely, the axis of symmetry is connecting the vertex, any vertex, with the midpoint of the opposite edge, right? Because there are 3 perpendiculars, like you guys are suggesting, that's the second one, connecting the vertex to the opposite edge, connecting the vertex to the opposite edge, midpoint of the edge, I should say, and boom. So there are 3 reflections, 3 reflections. Okay, so, okay, 3 reflections. Oh. 3 reflections. Usually I label them, give them names, but okay, we'll come to that in a minute. All right, so let's go ahead. What about 0 degrees? Yes, 0 degrees is the same as 360 degrees, and I simply call it I standing for identity. Some people, they represent it with the letter E. All right. Okay, next, which one do you want? The butterfly or the square? Probably the square, right? So let's check the butterfly in a minute. Okay, so the square next. So what are the reflections? Yes, I think by now you guys are getting the logic. A 90-degree rotation will perfectly be fine, because if I were to rotate this shape by 90 degrees, clockwise or counterclockwise, doesn't matter, the shape will exactly match to itself. A 45-degree rotation will make it like this, which is, nah, the shape should remain exactly where in the original position that it was before the reflection or rotation, right? So we have 4 rotations, and then 4 reflections, because, wait, do we have 4 reflections? I can see 2 of them. I can connect the midpoints of the opposite edges, and then I can reflect across the horizontal or vertical axis. What other reflections are there? Yes, there are also 2 main diagonals, and boom. So those are the other reflections. We should be careful though. The way the diagonal symmetries act on this object is quite different than the way the horizontal reflections act on this object. Similarly, the rotations are quite different than each other. So technically, the good way to analyze this is the following way. Just for the fun of it, let me show you. So suppose that you have this square, and let's label the vertices just to show you that these are totally different things. For instance, a 90-degree rotation, R90, will do what? It will send 1 to 2, 2 to 3, 3 to 4, and 4 will go back to 1. So that's the cycle notation of this symmetry, the 90-degree clockwise rotation. Do you guys see what I did? Started with 1, and okay, for instance, compare this with the 180-degree rotation. Well, 1 is mapped to where? If I apply a 180-degree rotation. 1 goes to 3. How about 3? Where does 3 go to? 3 goes back to 1, so it's time to close the loop. Open a new cycle. How about 2? 2 goes to 4, and 4 goes back to 2. So 2 goes to 4, 4, because 4 goes back to 2, so we can close the cycle. So that's a very convenient form for us. These are actually examples of permutations, right? Except that usually, I mean, we are familiar with seeing this permutation in a different way, right? So let me show you the way that you guys are most likely have seen it. So we have our set 1, 2, 3, 4. 1, 2, 3, 4. So when we look at R90, R90 takes 1 to 2, 2 to 3, 3 to 4, and 4 goes back to 1. So when I compare these 2 notations, actually there's a third notation. Let me show you the last one. R90 can also be shown like this: 1, 2, 3, 4. Okay, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1. Holy. So there are so many different notations for pretty much the same R90, right? Yeah, all of them are permutations. um, of our set 1, 2, 3, 4 onto mapped onto itself. But what does this notation emphasizes as you compare it to the other two notations? What is it that this notation emphasizes? Yes, yeah, that's right, that's right. Yeah, it emphasizes the loops, the cycles as we call them. Okay, so for instance, this one, look at how beautiful this notation is. It's telling you that there are two cycles of length 2 each. And so as a result, R180 is different than some other stuff. Well, okay. So let's, for instance, R180 is totally different than, let's call it, I don't know, let's call something A, for instance, totally different than this permutation, which sends 1 to 2, 2 to 3, 3 goes back to 1, and then 4 is mapped to itself. This one is also a 2 cycle, except that the sizes of those cycles are way different, right? As a result, these are different permutations. Yeah, okay, sounds good. For instance, if you look at R, let's say 270, let's check something interesting. So one, can you write it in cycle notation starting with a 1? It's customary to start with a 1. Yes, 270-degree rotation, which is the same thing as a minus 90-degree rotation, right? So meaning you can rotate it counterclockwise. Yes. So 1 goes to 4, 4 goes to 3, 3 goes, after you rotate it at 270 degrees, 3 goes to 2, and you close the loop. Yes, that's right. All right, so so you guys can see how those 4 rotations and 4 reflections, they are, so far what I did is I just looked at the rotations, but the reflections can be done in a similar way. For instance, we said that there are 4 reflections. If you look at this reflection across the vertical axis, usually I show the horizontal axis with the letter P, the vertical axis with the letter Q, the main diagonal here with the letter R, and then this main diagonal here with the letter S. So the 4 reflections in a square are PQRS. Yes, that's correct. If you have a regular polygon with n vertices and n edges, yes, so that would have 2 n symmetries. That's correct. N reflectional, n rotational. N can be odd or even, prime, not prime, doesn't matter. That's usually, this has a special name. So the symmetry group acting on a square is D8, dihedral group, if you want to search more on Wikipedia or some other sources, AOPS. All right, so yes, okay. So let me quickly show you the reflections. For instance, the reflection P will map, so if you want to show P in cycle notation, P will map 1, so can you guys write down P in cycle notation based on what we have so far? Let me just move it a little bit so you guys can see the screen. P is the reflection across the horizontal axis. Yes, so 1 is mapped to, yes, this is called cycle notation. Yes, 1 is mapped to 4. 4 is mapped back to 1, so we can close the cycle. Open a new cycle, you can pick any one, but we usually pick the smaller one. 2 is mapped to 3, and 3 is mapped back to 2, so boom. That's extremely convenient. In a similar way, Q can be 1 mapped to 2, and then 3 is mapped to 4, where 4 is mapped back to 3, and so on. So that's Q. But R and S have a different nature. R is, let's do it, okay, right underneath. Let me make it a little bit smaller space here. Oops, there you go. So R itself is, can you write R in cycle notation? So where does 1 go to? Under R. R is this diagonal, as you remember. So these recordings, today's class, are all available on Momentum Learning website. I mean, not website, but at the same time at the YouTube channel. Yes, 1 goes to 1, close the loop, then you open 2, 2 goes to 4, because if you reflect it, 2 will go to 4, 4 will be mapped back to 2, so there you go, and then 3 is mapped to itself, right? So 3 goes to itself, and that's pretty much it. Yes, order doesn't matter. When you write things in cycle notation, Okay, so order of the cycles don't matter, but order within the cycle might matter. In a 2 cycle, it doesn't matter, but in a 3 cycle, it matters. So for instance, whenever I write 1, 2, 3 versus 1, 3, 2 is different actions. So this would be a 120-degree rotation clockwise versus this one is a 240-degree rotation. 1 is mapped to 3, 3 is mapped to 2, 2 is mapped back to 1. And obviously you can write this in 3 different ways. You can write it as 2, 3, 1 or 3, 1, 2. That's okay. Usually that's, that's not how we do it. Okay, so let me just get rid of it. Yeah, that's okay. So, but down the road, it is for Burnside purposes, you don't need it. But especially when you do Polya, when you start counting the inventory, doing a general count, a total count in Burnside is quite easy, but counting individual cases is hard. So for instance, if I ask you how many ways can you color a square, a 2 by 2 square with 2 colors, black and white, 2 colors, black and white. You have an unlimited supply of blacks and whites, where up 2 color patterns. The question is asking how many coloring patterns. Now, coloring patterns is different than how many ways to color this object, a fixed object in space. What we are saying is this object can be rotated. If 2 colorings can be obtained from each other after a rotation, then they are really the same coloring, right? For instance, I think you would agree that this is the same as this coloring or this coloring. All of these colorings are the same because you can obtain one from the other using a simple rotational reflection. Yes, so you want to, so the question is, as a result, how many patterns? Well, yes, that's true. So yes, so there are 6 patterns, right? So here we are using no white, no black, 0 black. With 1 black, there's 1 way. With 2 blacks, how many ways? Yes, with 2 blacks, there's really 2 ways. Either those 2 blacks are next to each other or they are opposite. There's 2 ways to color it with 2 blacks. 3 blacks, how many ways with 3 blacks? And 1 white. 1 way, right? So you just put the 3, so you just decide which square will not be colored and everything else is, yeah. And finally, all 4 are black color. So there's really 1 way. So in total, like you guys said, there are 6 ways to color this object. So 6 coloring patterns on a 2 by 2 square. So the thing that I was telling you earlier about the cycle notation matters when you want to count individual subsets. If you want a careful count of every sub case, for instance, this case showed up 2 times. That's the only case. Then it's a whole story. Then you need an inventory of carefully putting down a list, which obviously you need to use algebraic techniques, which I don't want to go over here. Okay, so so far we did the square as well. Let's go to the butterfly now. So what are the symmetries acting on the butterfly? I tried to do my best. When I did draw the butterfly, what I was thinking is he has the butterfly, his eyes are just, let's say that he doesn't have an eye. Okay, he just have those 2 things. It's like a paper butterfly. Okay, it's not a real butterfly. This is a paper butterfly that I did do it. And I tried to draw these 2 wings as evenly as possible, and then those 2 wings as evenly as possible, but they are distinctly different than the main wings. And then it has this weird symmetric rectangular shape in the middle, and then it has 2 antennas. So the question is, how many symmetries? Well, obviously, like we said earlier, identity is always, you can always rotate this 360 degrees, and boom, that paper butterfly. But then there's another type of symmetry, like you said. So for instance, rotating it 90 degrees will always be, it will be a loser. How about rotating it 180 degrees? If I were rotating it 180 degrees, it will be distinctly different, right? So, it would look like this, which is obviously different than this shape. They are different butterflies. So we want to make sure the shape will look exactly the same. So there's no other rotational. That's correct. Identity is the only rotational. Are there any reflectional symmetries? Yes, that's across the middle of, like, perpendicular, right? This one, the vertical axis of symmetry here, if you reflect it, yes, that's the same thing, right? So you can call it R, so R. Or let's call it F, actually, F for flipping. F, flip. So this has two symmetries. You can think of your face. Usually they would say beautiful people have symmetric face, right? There you go. Obviously identity and this one, like, so his nose here, one dot is on that side, the other dot on the other side. Yes, there you go. The ears. But if he has a piece of hair on this side, oh shoot, he's no longer symmetric. He better shave these 3 pieces of hair, right? So have you read Dogman? My son wanted me to draw Dogman, and I started, no, not Dogman, sorry. What was the villain in Dogman? I forgot. Oh, no, not Catman. Oh, PD, yes, thank you, Tiger. Yes, it was PD. So he wanted me to draw PD, and I looked at a couple of sketches, and I started drawing PD like that, I guess. I think PD has eyes like that, and then his nose was like that, and he always smiles. There you go, that's PD. I think, yeah, this is our villain. But then, when he's angry, you can do the eyebrows like that, or when he's happy, he's, okay, so, but anyhow. But then my son said that I did a mistake. I forgot his whiskers. When you look at the picture carefully, whoever created the PD, his whiskers, 2 on one side, 3 on the other side. Really, PD is not a symmetric shape, face. He has weird stuff. But anyhow, yeah, Dave Pilkey, yes, that's the guy who drew it. It's really good. The same guy who did the Captain Underpants, or as I call it, Major Underwear or something. Anyhow, okay, back to our story. Oh gosh, this will be on YouTube, right? Okay, let's get back to business. Okay, oh yeah. So next is our necktie, which looks like a carrot or whatever you call it. So how about the symmetries of this shape? Yeah, it's the same, right? So this one, again, you can cut it in half, and again, the same reflection, and then the one. So how about, what else? A cross. What are the symmetries of a cross? Yeah, it's kind of interesting, right? So the cross has 4 rotations, just like a square, but then it has also 4 reflections, just like a square. In fact, you can think of it like a square, which you remove the 4 corners, right? So you just shave off the corners over here, 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 and then boom. You have the cross, which have 4 rotations, 4 reflections. Someone was saying earlier, how about the n-gons, right? So for instance, a pentagon, a 5-gon. Yes, 5 rotations, the rotations are there, and then 5 reflections. The reflections are clear as well. The reflections are just connecting the vertices with the opposite midpoint of opposite edges, just like the triangle, in a sense, because they have an odd number of edges. You guys see that? There you go. Here you go. So then you guys have, okay, let me just do it bold like that. So it has 10. The triangle is similar. You always connect the vertex with the midpoint of opposite edge, but the square is slightly different because it has an even number. Still, it has 4 reflections, but 2 of the reflections are non-symmetric. Like we have the horizontal, vertical, and the same thing will happen when we do the hexagon, right? Hexagon is also have different type of reflectional symmetries, as well as rotational symmetries. It has 12, 6 rotations, and then 6 reflections. But then the reflections would be, well, obviously the shape doesn't look really nice, but the reflections are like this, connecting two opposite vertices, the axis of symmetry here, the axis of symmetry there, and then you can have the axis of symmetry across midpoints of opposite edges, right? So this one and then that going all the way up to here. So again, but still 6, yes. Yes. Oh, someone is asking, how about the cross where we just do this? And not the cross, sorry. You have the square again. You do it like that. You just remove these two. So what are the symmetries applying to this square now? I mean, well, to this cutout shape. So this shape now has no longer these two. How many rotations, how many reflections? All right, good. Yes, 2 rotations, obviously the identity and the 360-degree rotation, and 2 reflections. 2 reflections. The diagonals no longer apply, right? Because, oh, sorry, the diagonals apply, R and S. But the P and Q no longer applies, because if I apply P here, after I reflect it across this horizontal P axis, it won't look the same shape. So that's why it is 2 reflections only. Oh, sorry, this one is 180. Thank you. There you go. A lot of people just corrected me. Awesome. So you guys are in pretty good shape. I think I'm pretty much done with all the symmetries, right? So I think as we have more and more cases, we can have a look at different types of symmetries, and then we can. Do you guys want to directly solve some problems? All right, you guys are ready? Okay. Oh, what is the Burnside lemma? Okay, let's first start by solving the problems without using Burnside lemma, and then when we are desperate, then let's introduce Burnside lemma. Let's try to stick as far as possible without using Burnside lemma. All right, so here we go. The first question is, suppose that I have this rectangle. Actually, let me draw it small, because otherwise I will run out of space. All right, so we have this rectangle which has 6 little squares in it, and I have do you want the hard question directly? Okay, let's ask the question that I had in mind. You have 1 red, 2 white, and 3 blue squares. How many different ways can you color this rectangle? Yeah, these are all squares. How many essentially different ways how many patterns, essentially different ways can you color this? Take your time. Let me give you about 3 minutes. Let me get my drink in the meantime. This problem, wait a second. I thought I made up that problem. Last night I was drawing a lot of problems. I said, okay, so which ones? Okay, I came up with several questions. 60 ways. Well, okay, if the shape is fixed, okay, if the question tells you that these squares are numbered, then yes, that would be the answer. The answer would have been 6 factorial over 1 factorial, 2 factorial, 3 factorial, 6, 5, 4, 3, 2, 1, divided by 1 times 1 times 2 times 1 times 2 times 3. These cancel. The 2 cancel here, 10, 60, yes. But that's not what the question is asking patterns, coloring patterns. So here, it would be correct if the question told you that this is something which is fixated on the wall. This is a nail on the wall and no one can change it. Suppose that this is a calendar for a week, 6-day week, and your mom or dad asks you to how many different ways can you color this picture, then yes, the answer would have been 60. But that's not the case here. We are told that you can rotate or reflect this shape. So it is kind of transparent because you are reflecting it. And it is rotationally, you can kind of rotate it as well. All right, so people started throwing a lot of answers. So some of you already solved it, good. Is the answer 15? No. Not 56, not 32, not 24, not 20. Okay, let me give you 2 minutes. Let me get my drink. Hold on. I was supposed to get my drink. Okay, I'm back with my drink. Okay, some of you guys are frustrated because I know half of the class already solved the answer. Yes, it's not 18, but it is. All right, so let's have a look at the question. I know, okay, a lot of you guys already solved the problem. Yes, it is 16, right? Yes, 16. Let's count all of them. So what type of how do you approach a problem like this? Cry, no. Case work, yes, cool cars on the run, thank you. Case work, what are the cases? And I'm really thinking of the red, right? Because where the bees are, come on, no. Well, I mean, yeah, I guess, but I think where the red is better. So how many cases are there for the location of the red? Yes, there are really two cases when you think about it. Red is either here in one of the four corners, or red is, okay, I'm so lazy, I'm from now on, I will draw the shape like this, or it's in one of the center squares. You might say, wait, Dr. Nal, how about the case where R is over here? Don't worry about it, because you can just reflect the shape across this axis and boom, you can map R over there. So technically it's the same thing, right? The same way I can rotate this, reflect this, or rotate, doesn't matter. Rotate it 180 degrees and boom, the R can be over here mapped. So it's technically the same shape. All right, so there are two cases. Let's start with which case? This case. How many ways to color it if R is in that corner? No, it's not symmetric, so it's not 8 and 8. Yeah, this case, there's 10 of them. And what are they? 5, choose 2. There are 5 squares left. We have 2 whites. Just choose 2 locations for the white and boom. Suddenly you might say, hey, Dr. Nal, is it possible that we are double counting some of the colorings? No, because there's no way after I rotate or reflect, except the identity, that I will get back to this shape. Why? Because R is located in a non-symmetric position. All right, because R is located in a non-symmetric position, there are 10 colorings here, or patterns, whatever you call it. Coloring patterns. Okay, there you go. Coloring patterns. All right, so the second shape is different though. The second shape is, you can't just say it's 5, choose 2, because it is not. So for the second case, how do you count it? Yeah, the other one, you probably can list all of them because it is super small. Yes. So just list. Oh, thank you. Okay, so just listing all of them would do, right? So let me go ahead and actually list them, I guess, because, I mean, yeah. So let's just, it's not too hard to list them, right? So, well, because I have 2 white, let's just draw, and 3 blue. Okay, the white, I will do it with dots. And then the blue, nothing. All right, so where can I put the 2 dots? I can put the 2 dots next to the R. So the dots are the whites, okay? Or I can put the dots, I don't know, like that. There's no dot here. Do you see that? Or I can put the dots, I don't know, one side. I can put the dots, okay, what else can I do? Oh, yeah. This is different too, right? This is totally different. Now, can I do it like this? Is this different? R and then 2 dots over here. Yeah, that one won't work, right? So because we already counted this case over here, technically these are the same colorings. Yeah, they are the same patterns. So you definitely, by the way, coloring patterns is a huge research area, right? So they're still mathematicians. You know, mathematician is not that bad of a job after all. You can just, if you enjoy shapes in nature and things like that, you can discover so many things. In fact, oh, I should have said this at the beginning, right? And in the meantime, you guys figure out how, what are the other two? I have no clue. Okay, let me check my notes. What are the, they can be like this. Yes, yes, yes. Like that, I guess. I'm missing one. And I'm 1 and 6. Oh, 1. Oh, yeah, that's true. 1 and 6. Yes, thank you. Yes. I was about to tell you guys that, did you know that these concepts, symmetry, is used in organic chemistry, for instance, or chemistry in general? Forget about organic, right? Have you ever, if you have internet in front of you right now, just type in glucose. Glucose, you know what it is, right? C6H12. Oh, wait, was it what? What was the number here? 06, right? So yes. So this is food, right? I mean, this is sugar, kind of simple sugar, but there are so many ways you can symmetrically connect those carbon, hydrogen, and oxygen atoms. And I think they call them isomer. I'm not sure how they call it, isomers. And yeah, so that's interesting. Quantum physics, that's all they do, is they just look at symmetry of the protons, the photons, or whatever. I have no clue what they do in quantum physics, but I know very well they do a lot of these stuff. Yeah, it's pretty exciting. Well, the most exciting story is how it all initiated. So the very last question we will solve will be related to that. It's kind of strange to imagine that you would think that something which is about symmetry would be initiated from geometry or something like that, right? But in reality, it started with solving polynomial equations. How in the world do you use symmetry in solving polynomial equations? I mean, symmetry between the roots and so on. All right, because this is visual, usually we prefer coloring like that. Like coloring problems are places where we can use symmetry a lot. Okay, anyhow, so somehow we ruled out 4 colorings here, right? So what the ones that we ruled out are the, if you wanted to do, this is case word counting. Alternatively, you could have done complementary counting, ruling out, so we said that, so there are 6 here. Alternatively, we could have said, so what are the ones that are repeating? Well, obviously this is a repeat. It repeats with this one. Another one which would be a repeat would be, so R, how else? Oh, this would be a repeat as well. It would repeat with this one, right? So that will counting twice. Why is the rest 5 choose 2? What do you mean, why is the rest 5 choose 2? The rest, you mean, no, 5 choose 2 is this one. This case is 5 choose 2, 10. And then this case, the second case where R is at the center. So R is either in the corner position, and there are 4 corners, or it's in one of the central positions. Why are we choosing 2 whites from 5 boxes? Oh, well, because there are 2 whites and 3 blue. The ones that I didn't color are the blues, basically. We are, yeah, 5 choose 2, yes. Because it isn't symmetric. Yes, this shape is not symmetric. That's why it's 5 choose 2. And if you feel confused, that's perfect. But you can list them out. The good thing about this is 16 is not a big number. If you don't believe me, you just list them out and then convince yourself. You can even have a paper pencil. Just cut out some papers and then just do your magic. And then try to figure out what the symmetries. All right, so apparently there's 2 more that we ruled out, right? What are the other 2? Oh, yeah. I know one which is symmetric to this one, right? So we have an R, and then this, we ruled out that one as well, because it's just a repetition of this. Oh, and then there's another one which we ruled out related to this one. R, and then a dot here, a dot here. So technically they are the same. So these 4 are ruled out. All the others are remaining. So if you wanted to do complementary counting, you could have done 10 minus 4. No. Wait. Okay. I think the way I showed the solution, I pretty messed up, right? So the answer to this question, how many patterns where they are indistinguishable, these squares, except their locations, then the answer is 16. 10 in this case, and then 6 in this case. So if you wanted to use case work, you could have listed the 6 like the way you did here, but alternatively, you could have done complementary counting where you said for the second case, you could have done 10 minus 4. So that would work. Okay, so now what is the benefit of using Burnside? Let's quickly apply Burnside to this problem, I guess. So in the meantime, we can learn how to use Burnside's lemma. Well, okay. Or actually, this is not a good problem to apply Burnside's lemma. Okay. So forget about Burnside lemma. Let's solve a couple other problems and then let me introduce you Burnside lemma. Do you want, how about this question? Okay, so let's do the cross. So the cross here, 5 squares, and we are told you have 2 white, 2 black, and 1 red. So how many ways can you put those such that you have a different, how many different patterns, like essentially different coloring patterns, which are different, where up to rotation and reflections. Yes, you can definitely do a case work again. Case work on red would be the best. That's exactly what I did, I think. Actually, the first time I counted it, I counted it wrong. Thanks, because I kind of confirmed the result with Burnside, and then after that, it made sense. All right. So how many did you get? Not 5, not 8. No, it's not 8. Sorry for that. Not 4. Not 10. Not 7. Okay. Half of you already have not 12. Yes, it is 6. I think it is 6. Let's do a case work for the red, right? So that would be a case work. So what are the cases? How many cases are there for the location of the red? Really 2 cases. Either red is at the center or red is one of the sides, which it doesn't matter. Afterwards, you can just rotate it or reflect. You can always get a similar shape. All we need is now to count all the cases where red is at the center. And how many for red at the center? How many ways can we put the remaining 2 colors, 4 colors, 2 white, 2 black? Yes, we can either have the white opposite each other and then black opposite each other like this, or red is at the center, white and white are like that, black and black are like that. Do you guys agree? Yeah, that's pretty cool. Or if red is on the side, now let's do the red on the side. Well, the white can go like this, and then the 2 other will be the blacks. Or when red is on the side, we can have white next to each other again, but in this configuration, and then these are the blacks. Or again, red is like this. Okay, I have no clue what are the other 2. Okay, so let's think about it. Maybe white is not in the center, right. Yeah, so white is either like this, the remaining 2 cases, or white is like this, and the remaining are the blacks. There you go. So you have really 4 more. So in total, 6. All right, I think it's time to just go ahead and, okay. Do I have other? Yeah, I have quite a few examples. It's very easy to come up with examples for these problems. I think there was a couple years ago, there was an AMC 10 problem. I don't know if you guys remember it. It was a really, I thought easy question. Do you guys remember this question? Again, there was 2 green, I think, 1 red and 1 blue, if I remember it correctly. Something like that. 1 red, 1 blue. You have rotational and reflectional symmetries. Yeah, paper triangles, yes. Rotational and reflectional symmetries. How many different ways? The use-sum problem was different. Wait, the use-sum problem was, wait. Yeah, there was a use-sum problem. It doesn't show up too much on the use-sum. Burnside lemma is just one of the simple tools that you use, like to stitch the pieces together. By itself, it's not anything, right? Unless you are doing serious research in the idea. You just don't want to just, Burnside lemma is like, I don't know, like it's a tool that you have it handy, like symmetry, and then you use it when it is useful. And then, oh, that was AMC 8, okay. Yeah, how many coloring patterns are there? Yeah, so okay, so you guys can look at all the cases. You can do a case work based on I don't know. I think based on where the location of the two greens is, because suddenly it's different than the other two. The other two are so symmetric. That might be one way to do it. There's only 3 ways. Okay, so most people say the answer is 3. Is that correct? Okay, so we might have 2 green like this. If green is at the center, then the red and the blue go to opposite directions. Or the green is not in the center, which means they are like that, after which either the red goes here and the blue goes here, or green is again like this, blue goes here, red goes here. Okay, so there's pretty much 3 different ways. All right, so let me ask you one of my favorite questions. I mean, you've probably heard me asking this question. Actually, wait, I think I already have a YouTube video about it. Okay, so let's not go into that. Okay, quickly today's subject. So what is Burnside formula for counting all this stuff? Burnside formula. Well, the formula is the following. So suppose that you have this 3 by 3 square and you want to color it using 2 colors, black and white, and you have unlimited supply. It's not like in the previous question where you have 2 white, 2 blue, and 1 red, and so on. So where you have limited amount of each one. No, you have unlimited amount of each one. How many different ways can you color it? If the shape was fixed in space, the answer would have been 2 to the 9. Each square has 2 choices and 2 to the 9, but the shape is not fixed in space. There are 8 symmetries which are acting on this shape. So as a result, the formula says the following: 1 divided by number of symmetries, which is 8. Okay, let me first write the formula. Number of symmetries, and then summation of the fix of the symmetry. There you go. Okay, so this is a weird formula. 1 over, okay, let me go over it. So 1 over 8. We open a parenthesis because summation means we need to add up a lot of stuff inside the parenthesis, okay? So we will go ahead and add quite a few stuff. Maybe I need even a bigger. So for each symmetry, apparently, sorry, like that. So for each symmetry, we need to add stuff. And because we have 8 symmetries, there will be 8 terms inside this bracket, inside this parenthesis, right? So maybe I can put 4 of them on the first row, and then 4 of them on the second row. There you go. So that's an easier way to fit everything into that parenthesis. There you go. All right, so the 4 rotations, we need to find, so the 4 rotations are 90-degree rotation, 180, and 270. So let's start with the rotations. Starting with I, how many of the shapes will be fixed? Sorry, how many of the colorings, my bad. How many of the colorings will remain unchanged if I were to apply the identity symmetry? So this is kind of the idea. So any coloring will remain unchanged, will remain as if it is fixed in when you look at it, like straight looking at it. If you just apply nothing to it, like identity, of course the shape will remain unchanged. So all of the colorings, which is 2 to the 9 colorings, all of them are acceptable. All right. And kind of this gives you the idea of what will happen next, right? Here, these are just adjustment terms. So technically what we are doing is the following. Technically, the answer you are thinking should be very close. The number of patterns, coloring patterns, should be extremely close to 2 to the 9 over 8. Do you guys agree? Very close to 2 to the 9 over 8, because it makes sense. There are 2 to the 9 colorings, but probably you are overcounting by a factor of 8. So we just need to divide by 8 because there are 8 symmetries. So you might think that each symmetry creates a new copy. So as a result, it's just divided by 8. But it's not quite so, because some of them won't create 8 copies. For instance, white, and everything else black. This has only 2 copies. This one and this one. Let me show you. White, and then black. This has only 2 copies. So if you were to divide by 8, you would have made a mistake on this one, right? You should have really divided it by 2 instead of 8. So that's why we need to make adjustments to our formula, basically. And that's exactly. The rest of the terms are adjustments. So technically, even if you don't know Burnside Lemma, you can guess the answer. All you do is write out that and then divide. So you guys can more or less guess it's close to what the answer will be close to. So this is 512 divided by 8. So you said 64. So the answer will be slightly more than 64. I have no clue what the answer is. So some of you guys are saying it's 77. Yeah, probably. All right, so let's quickly check. So we are done with I. Next, 90 degree. How many of the colorings will remain unchanged if I were to apply a 90-degree rotation clockwise? How many of the colorings would seem to remain unchanged if I were to apply a 90-degree rotation? For the shape to remain unchanged or seem to remain unchanged, whatever is the color here, let's call it color A, this one better be the same color, because after a 90-degree rotation, this one will go over there. But then whatever was over here better be the same here as well. And whatever is here better be the same here as well. So those four corners better be the same color. If after rotating by 90 degrees, I want the shape to remain fixed or seem to remain fixed, that's how. Similarly, B here and C here. So really, we have to choose the color which will determine the A. We have to choose the color which will determine the B. And finally, we need to choose a color for C. Yes. So there are two choices for A, two choices for B, two choices for C. That's 2 cubed. Do you guys agree? Wow. So if the answer is 102, then it means my approximation is horrible. Well, it is okay. It's not that good, maybe. All right. So everyone agree on this one. Next one is, and you guys, okay, next one is 180-degree rotation. So after I rotate this shape by 180 degrees, this guy over here will be going to this here, right? And because I want the shape to remain remain fixed, at least I want to see it fixed. So this is A, this is A. So they better be the same color. If this is a B, after I rotate it 180 degrees, this will be a B. This is a C, that has to be the same color. This one, if this was a D, then this better be a D as well, and this one is an E. So only patterns which are of this kind will remain fixed after I apply a 180-degree rotation here. So this is 180-degree rotation. Do you guys agree? And yes, I have to choose a color for A. There are two choices. I need to choose a color for B. I need to choose a color for C, a color for D. So 2 to the 5, yes. 270 degrees is pretty much the same as 90 degrees. It's like minus 90 degrees clockwise. So this one is also 2 cubed. Next, let's have a look at the reflections. Let's first have a look at the horizontal reflection. So because I want to see the coloring pattern remain fixed after I apply this reflection across this axis over here. So whatever color this one is, better this one be the same color. Whatever color this one is, better this one be the same color. Whatever color this guy is, better this one be the same color. Well, this one will be mapped to itself, so this can remain whatever it is. This you can freely choose what it is. You can freely choose what this is. So really there are 6 choices here. Do you guys agree? So this is just 2 to the 6. The same way for the vertical reflection. Now finally the diagonal. Okay, I'm not using my space wisely today. Okay, so this diagonal over here. Well, this guy will be mapped to itself after I reflect across this axis. These two will be mapped to each other. These two will be mapped to each other. This one will remain as it is. These two will be mapped to each other. And then this one will remain where it is. 6 letters. We will make a choice of factor of 2 6 times. So that is 2 to the power 6. And the remaining one is also 2 to the power 6. And that's it. That's the answer. As you can see, these are smaller than 2 to the 9 by a significant factor, but 2 itself is such a small number. That's why we are very much off in our prediction. Okay, this is 102. Thank you. But if instead of 2 colors, if there was 10 colors, 10 to the 9 is significantly larger than 10 to the 6, right? So all that will change in the formula will be the following. If there were C colors instead, so you can just change the number 2 here with the letter C's. Do you see that? And boom. And that would have solved the problem. I kind of enjoy this a lot because suddenly this has a lot of connections to algebra. What it is telling you is the following. If I gave you a polynomial like this, x to the 9 plus 4x to the 6 plus 2x cubed plus, let's first write x to the 5. Plus x to the 5 plus 2x cubed. What can I ask you about this polynomial? Show something about this polynomial. What is it? Why do you multiply? Because by 1/8, that's the formula. That's the formula. Burnside's formula says number of patterns is given by this formula. All I did was just apply the formula. So why did I ask this? Well, oh, sorry. What do I want to ask about this? I want you to prove algebraically that this is divisible by 8. Because technically, if this is the number of coloring patterns, it works for any C. If X is an integer, this is an integer, but it's not obvious why this polynomial should be divisible by 8, right? Apparently it must be. Otherwise, Burnside Lemma will give you a non-integer, which is absurd, right? So yes, you guys can check this modulo 8 and see if it is congruent to 0 mod 8. Or, okay, some of you guys are suggesting that we can just factorize this pretty quickly as well. So yeah, either way works. All right. How is it, what? How is it 102? I don't know. Whenever it is 2, is it 102? 2 to the 9 is 512. This one is an 8. This is a 32, 8, 64, 64, 64, 64. Add all these 8 numbers and divide by 8. Oh, okay, so it's 102. Good. So now let's go ahead and do you want to solve, for instance, okay, so whenever you have unlimited colors, applying Burnside Lemma is relatively straightforward. But if you have limited number of colors, then you need to use Burnside Lemma carefully. You need to use, how is the polynomial what? How is the polynomial related to Burnside? The one that I showed you? The one that I showed you is the following. The way it is related is the following, because we realized that if the question was more general, and if the question was asking, there are C colors, how many patterns to color this shape, a 3x3 grid, how many essentially different colorings, then the answer would have been this with C's over here, right? So C, 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 all this weird stuff. So all I did is C to the 9, that's like X to the 9. This one, I have 4 C6s, so 4x to the 6. I have an x to the 5, and then 2x cubed. Apparently, because when after I multiplied with 1 over 8, which is the same thing as dividing it by 8, that comes out as the number of coloring patterns. But the number of something is obviously an integer, right? So technically what this is suggesting is this polynomial is divisible by 8. So that's a weird thing, right? So this is one of the corollaries, like one of the side benefits of Burnside. Sometimes if you want to show a polynomial is divisible by a number, so you might just try to create a shape and then, so anyhow, let's, for instance, this, do you guys remember this earlier question we did here? Let's apply Burnside Lemma to this one. Obviously, I don't have to apply Burnside Lemma here. It is, it's obvious. But this one, so for instance, if, how many ways over here, oh, sorry, there's more questions. Oh, wow, you guys already factorized it. Perfect. Some of you guys already factorized the polynomial that I showed you, and then you guys already showed that it must be divisible by 8 for such and such reason. Okay, fine. All right, so you guys can do it definitely. So for instance, if I ask you, what are the, for instance, let's apply Burnside Lemma here on the first case. Well, when R is over here, what are the axes of symmetry? What are the symmetries of this shape, which has, on one corner, it has a red color. How many symmetries does this shape has? A rectangle with a red on one side, one corner. That has one symmetry, and it is the identity. So if you wanted to apply Burnside Lemma on this one, which would be extremely silly, it would be 1 over 1 because there's only one symmetry applying, 5 choose 2. Because only identity will fix it, and identity has 5 choose 2 ways to color the remaining. Okay, that's extremely silly, but we can definitely do this case, the second case. Now, when red is at the center, what are the symmetries acting on this? What type of symmetry? Sorry, let me do it again. What type of? Oops, sorry. Sorry for that. So, what are the symmetries of this shape? R. Yes, this shape has 2 symmetries. It has identity, meaning 360-degree rotation, and the reflection across this axis. Yes, and then a reflection. Let's call it F. So therefore, if you want to apply Burnside to this, it would be 1/2, open brackets. So how many of the colorings will remain unchanged if you were to apply identity? All of them. How many is all of them? 5 choose 2. Color it whichever way you want, right? So color with impunity. Color whichever way you want. Plus, then how many fixes of F? A reflection. Well, whatever color this guy is, better this one be the same color. Whatever color this one is, better this one be the same color, and this one can be any color. Now we should be careful. Why? Because we have limited number of colors. We have 2 white and 3 blue. 2 white, 3 blue only. I can't just naively say so many such and such choices. So we have a restriction here. Because there's an odd number of blue, one of the squares has got to be a certain color. Which one is it? The A, the B, and the C. The C has got to be which color here? It has to be white, yes. Do you guys see that? So in a sense, Burnside Lemma is the opposite of counting distinct patterns. In Burnside Lemma, we on purpose try to find the symmetric patterns, and then we make adjustment. Like we adjust for that, and then we divide by 8. Versus in what we did here is try to constructively create each and every single one of them, which is a hard business. Obviously, it's tough. All right, so this one has got to be white. Now A and B has 2 choices. Either A's are white and B's are blue. Oh, sorry. This one is a blue. Sorry, my bad. That's a blue. Yeah, sorry. All right, it's a blue. All right, yeah, either A's are white and B's are blue, or A's are blue and white. So really this is a 2. Do you guys agree? So that would be 1/2, 10 plus 2. And that is 12 over 2, which is a 6. Yay! All right, now, yeah, okay. So let's go over a couple other questions. So if there is no restriction in terms of color, Burnside is lifesaver. So you guys can check my YouTube channel for more details about that. Let's solve a different type of problem now, something which I don't think is in my channel. So you guys can have a look at that later on. So if I ask you, let's draw some graphs now. Now this is a harder problem. So we will be looking at essentially different looking graphs, okay? Why are we splitting into cases for that problem? Because it was the natural way to go. Yeah, so case work, because we have a limited number of colors. Whenever you have a limited number of colors, you have to have a case work and then apply Burnside Lemma to each cases separately. I mean, do you want to see that question also on Burnside? I mean, it is silly, but so for instance, we could have solved this question using Burnside Lemma as well. I mean, so yeah, but yeah, so sometimes the cases would be, would end up being silly. Yeah, do you want to see Burnside Lemma on this one? Okay, let's quickly check Burnside Lemma on this one. All right, so let's do Burnside Lemma on the case where, again, we have a limited number. Okay, so here we go, 1/8. Okay, so let's do it without casework. I would personally do a Burnside Lemma with casework after I place R at the center, or after I place R. So we can either do 2 separate Burnside Lemma to these 2 subcases, or we can directly use Burnside Lemma, but in general, it's harder. Okay, let's quickly do it. So how many of the colorings will remain unchanged after I apply the identity? Yeah, there's a lot of questions. So yeah, don't worry about those. Yeah, how many of the colorings will remain unchanged after I apply identity? Yes. Oops, come on, just move out of my way. Okay, there you go. All right. Yeah, so it would be pretty much all the colorings, which is 5 factorial divided by 2 factorial, 2 factorial, 1 factorial, right? All of them. Plus, how many of them will remain unchanged, which will look exactly the same after I apply a 90-degree rotation, 90 degrees? How many of them will seemingly look alike after a 90-degree rotation? Yeah, this one is hard to envision. Well, first of all, the red should be at the center for sure, right? Otherwise, yeah, it would. But then the 2 white, that white will be mapped to that white, but that white should be mapped to here. It won't happen, right? There's really 0 ways. 90-degree rotation, not gonna happen. And similarly, the 270-degree rotation, not gonna happen. But 180 can happen. 180-degree rotation can happen. How? How many ways? Yes, in two ways. Either I have whites here, or and then these are the blacks, or the other way around. So the red at the center, and then blacks over here, and then the whites over here. Do you guys see that that's two ways? All right, so next are the reflections. Holy, okay. Okay, so for the reflections, okay, let me just get rid of everything. All right, so we have, well, obviously the two type of, the P and the Q are similar, so I will just multiply the P by 2, and then I'll do the diagonal. First, let's do the horizontal reflection. So whatever this one is colored, that one should be the same color, and then we have B, C, D. These can be any color you want. How many ways can we have this situation? Not 2. Wait, unless it is 2. Yeah, I think, yeah, not 2, not 3, not 4, not 5, but 6. Yes, it is 6 ways. How can it be 6? Okay, let's quickly check. So, well, let's start concerning ourselves with the red. For sure, red cannot be on the location of A for sure, right? A is either a white or a blue for sure. So once you choose what the color of A is, which you have 2 choices, either both of these A's are white or both of them are black, you have 2 choices there, then red can be any of the 3 here. So there's really 6 ways. You guys see that? And finally, 2 times let's do it over here. Finally, this diagonal over there, remember there is nothing here. These corners are empty. All right, so again, we have 1 red, 2 blue, 2 black, 2 blue, 2 white. I mean, two blue, 2 white. So reflection axis is this one, this diagonal. Well, whatever this guy is, this better be the same number. I mean, color. This better be the same color. And then this one is its own color. Well, when you look at it like this, yes, it seems red has to be the center for sure. And then A has 2 choices. If A is blue, then B's are white. And then if A's are white, B's are, okay, so there are really 2 choices here. And done. That's it. Well, obviously this is, yeah, doing it with 3 colors, the case work, you can see how tricky it can become. That should give you exactly the 6 again. But personally, the way I usually end up doing, if you have a limited number of colors, so this is, you have an inventory basically of colors that you can use. Why 6? Which one why 6? The answer? Because you just plug it in and you get a 6. Or do you mean that 6 over here? I'm assuming you are asking me for this 6 over there. Oh yeah, okay, so this 6, let me explain again. So we are checking the this rotation across the horizontal axis. We just realized that because these 2 A's better be the same color, and red is an odd number of colors, we have only 1 red. So meaning the 2 A's here are either both white or they are both blue. Huh? Do you guys agree? The A's are either both white or both blue, so there are 2 choices there. And then B, C, D, for one of them, I need to choose where the R is. So it has 3 choices, and the remaining 2 letters would be the color that we didn't use. So 2 times 3 is 6. So 6 ways over there. All right, so let's go to graphs now. All right, so graphs. This is such a fantastic thing. So a graph is a picture where you have a bunch of dots, which we call as vertices. And some of these vertices are connected by edges like this, for instance. This is not a vertex, not vertex. Okay, so a vertex is clear. At the beginning, you already know what your vertex is. But obviously, this graph can be represented in another way as well. So for instance, if you label these 1, 2, 3, 4, 5, you might as well just change them. Really, this shape is the same as this one. Oops, come on. Where you start at 5, 5 goes to 3, 3 goes to 1, or it has a neighborly relationship with 1. 1 has a neighborly relationship with 2. 2 has a neighborly relationship with a 4. Yes, these 2 pictures, believe it or not, are the same. So in a graph, what matters is the neighborly relationship. All right, so we show that neighborly relationship with an edge. So either between any 2 vertex, there's an edge, or there's no edge. Awesome. And usually a graph, if all the edges are intact, all of them are still there, we call this, isn't this graph theory? Yes, but yeah, Definitely. But this is extremely simple. I mean, I'm not doing like super advanced. Like you guys can check. Poshanlo is sharing his doctoral level graph theory class on YouTube. If you haven't watched it, you guys might just as well look at that class for a few minutes. I mean, it is very challenging, right? But anyhow, yes. So we have vertices and edges. All right, so how many, let's start with, what do you want to start with? Okay, let's start with a graph with one vertex. How many graphs with one vertex can there be? How many of them? Number of graphs, essentially different graphs. Where really, when I mean by essentially different graphs, I don't label the vertices, basically. I don't want to, so because these two graphs are the same, I might as well just remove the labels, right? So that's exactly the same graph, basically. Yes, there's only one graph. How about a graph with two vertices? So number of vertices is 2. How many graphs are there? You have 2 vertices. How many different relationships can exist between those two people or 2 dots? Either they are friends, after which I connect them, or they are foes, after which they are disconnected. So there you go, you have really 2 ways. That's it, there are 2 graphs. All right, friends, no friends, there you go. How about 3 people, 3 dots? How many type of graphs are there? Let me give you a few minutes. Yeah, this thing can become easily complicated. So I want to open my list in front of me so that I don't mess up this one. Okay, yeah, I have my list in front of me. Okay, how many? You guys are saying 8? No. 4, yes. Let me actually draw it like a triangle. Either all 3 are enemies of each other, like that. That's one way. So here there was 2 graphs, right? 2 graphs of this one, like that. So we did that case. Now we wonder how many here. So or all 3 are connected, or 2 of them are connected, one of them is still out there, or you have 2 connections like that. You guys agree? So we have 1, 2, 3, 4. Anything else is so 4 graphs. Obviously, as the number of vertices increase, that will the number will start increasing. I think exponentially or something close to that. Wait, it can't be exponential. I think it is polynomial. Wait, it is it exponential or polynomial growth? I don't know. All right. I think it might be exponential. Yeah. All right, so let's do it. G equals 4, the first interesting question. Let me open a whole new space. I love this question. And then we will look at some interesting stuff about G, the one with 4 vertices. All right, people. I'll ask you 2 types of questions now. So the first one is, let's first create all of them. Okay, here goes one where all of them are, there is no edge. Why don't we just count the number of edges, right? Casework, right? Casework based on number of edges. I think that's a good way to classify them. If there's no edges, there's really one type of graph, like that. What about one edge? How many graphs are there when there is one edge? There's only one type. But then if I ask you, someone is saying 6. I think what Brian is saying is there are 6 labelings. Okay, that's another thing. Okay, so let's have an, okay, I'll count this next. Okay, because Brian brought that up. Okay, so this one is type of graphs. Okay, I don't want to confuse anybody. Let's just call it type of graphs. There you go. We have really 1. Okay, how about 2 edges? How many types of graphs are there? Yeah, so for the first time now, it seems we have 2 types. Yes, either they will look like this, 1, 2, or they would look like this, 1, 2. Do you guys see that? So let me do it like this. So this is a subcase. There you go. We can count them separately. All right, so we are done with the case of 2 edges. Let's do 3 edges now. How many ways can we have 3 edges? What if they intersect? It's still the same thing. Intersections doesn't have any meaning. So for instance, this is the same as this one. So these two are the same thing. All right, so technically they are the same. This is irrelevant. So this is, yeah, that intersection point doesn't mean anything. All that we care is two of them are friends, and then the other two are also friends amongst themselves. Yeah, that's pretty much it. Here, this is a different situation where we have one guy which is very popular, this guy who is like a geek, and then the other two are mildly popular. Yeah, so, all right, so 3. Yes, we might have, oh wow, you guys saying 3 different ways? 1, 2, oh yeah, 3 ways, that's correct. So either they are like a triangle, I guess, or it might be like a road like that. And obviously this is the same thing as this one, right? So these two are the same thing, so it's totally irrelevant. So because, all right, and then what's the last one? Oh, this one, right? That, and that. There you go. Okay, am I losing people here? All right, so I hope not. Okay, so 3 of them. Okay, we will count each one, how many labelings of each one. So that will be a fun thing to do. Don't do it in real life. Okay, finally 4 edges. No, not finally. The max is how many edges? That's no final. We have a lot of other cases. How many 4 edges? Yeah, the max is 6. We can have up to the complete graph. K4 has 6 edges. Here, this one, it has, for that one for sure. What else? Do we have any other? There's one more for 3. Which one? Wait, 3 has one more? 1, 2. No, I don't think so. Yeah, my list has, no, there's no other for 3. Yeah. All right, so there's one more for 4. Do you guys find it? Come on. All right. So the last one for 4 is the following. You start with a triangle, and then one of the vertices is also further connected to that guy. So these two are essentially different. There you go. The 5 is only one of them, right? So we can already guess what it is. It's just removing one edge, right? Just remove one of the edges and yeah, that's it. No, that's the same thing. Yeah. All right. And finally, the 6 is the complete graph. There's only one of that. And the labeling is also unique. All right. So you guys are ready to start counting the labelings? Holy, it will be quite a show here, right? Okay, so we are counting how many different ways we can label a graph which looks like this. Okay, how many ways? Oh, labelings means I'm going to use the letters 1, 2, 3, 4. How many ways can I put the letters 1, 2, 3, 4 into this graph to represent that graph? Yes, that would be one way. Just put 1, 2, 3, 4, right? There's really one way to do it. If you exchange 2 and 4, that's still the same thing because you have 4 independent vertices. What matters is the way the edge relationships connects the dots. Okay, now how many ways can you label the second case, one edge? This case over here. How many ways? So here, remember that 2 of them will be friends, and then 2 of them will be enemies with themselves. Yes. So first we need to choose who are these 2 good friends, and we have 4 choose 2 ways to decide who are the good friends, and then the remaining 2 will be just themselves. Hey, that reminds me of something. What does it remind me? Yeah. Okay. So yeah. All right. So doesn't this remind you of the cycle notation, where this is its own cycle, this is its own cycle, and then these 2 are going between? Well, but then that would be yeah. That's not a good way to think about this. All right, don't think it like that way. Okay, good. All right, let's do this one. Next one. How about this case? There's another way for the 5. Seriously? Okay, yeah, I'll check that in a minute. All right, so this case, first we need to choose the popular guy. How many ways can I choose the popular guy? 4 ways, 4 choose 1 ways to choose the popular guy. And then I need to choose the 2 people connected to that popular guy. How many ways can I choose those 2 people from among the remaining 3? Yes, 3 choose 2 ways. And then that guy who is on his own, that vertex, which is, that's one way you could, or alternatively, you could have said 4 ways to choose the lonely one, and then 3 ways to choose the one in the middle, and then the other 2 are automatically there. Okay, that's it. How many here? 12. Thank you. Next one. How many graphs like this? Wait. That's very similar to this one, I guess, right? Okay, so there is a big debate in the chat box. Half of the class says the answer is 6. The other half says the answer is 3. Is it a 3 or a 6? Let's list them, right? So let's list them. Either, so this is the only way we can have the settle this thing. So I can have 1 and 2 friends, 3 and 4 friends with each other, or 1 and 3 are friends, and 2 and 4 are friends. That's the second case. Or I can have 1 and 4 are friends, and then 2 and 3 are friends. That's it. That's really the only way. There's no other way you can have friendly relationships in this structure. It is different than this case simply because, okay, let me list out all the 6 here. Either 1 and 2 are friends, and then 3 and 4 are like that, or 1 and 3 are friends, and 2 and 4 are like that. 1 and 4 are friends, 3 and 4 are independent, or 2 and 3 are friends, 1 and 4 are independent. And you guys are seeing where I'm going with this, right? To the right. 1 and 3, and finally 3 and 4 are friends, 1 and 2 are independent. Do you guys see that this is different than this? So this is really 4 choose 2 divided by 2. So because this creates, there's a symmetry there as well. The groups themselves are symmetric with each other as well. Here they are not symmetric. It has 2 components, but the components are different. They don't look alike. Here the components look alike. I said 4, 1, 4, 3, 4. Oh, I messed up over there. 1, 4, 2, 4. Oh, sorry. 1, 2, 3. 2, 3. Thank you. There you go for the record. For future generations, when this is available, we want to make sure everything is covered. This is still peanuts. We didn't come to the real big problem. Okay, we probably don't have that much time, but okay, so 3. This is, how many ways can we label this? Yes, so we choose which guy is lonely, which we can do it in 4 choose 1 way, and then the rest they are a union. That's it, 4 ways. How about this one? How many ways can I do this one? Nope, not 6. Nope, not 6, not at all. So how many ways can I create a chain like this? How many ways can I label a chain like this? So you guys are saying only 6 ways. I think there's much more than that. Well, not much more, more than that. Yes, 4 choose 2 ways to first choose what are the endpoints, and then what? Once we choose the label of the endpoints without loss of generality, let them be 1 and 2. 4 choose 2 ways. First, identify those 2 endpoints. Then the remaining 2 labels still have 2 choices. Either this is a 3 and this is a 4, or this is a 4 and this is a. Remember, we are counting labelings here. Thanks to Brian. I wasn't planning to do this today, but okay. So there you go. So times 2 here. So we have 6 times 2, 12 ways. Yes, that's right. Next, this one. And by the way, the overall sum of all the labelings, how many should be the overall sum of everything? Among all these graphs, how many labelings should there be? Like when we have finished all the cases, what number will we get? That's total surprise too, huh? Okay, so this one, how many ways? This one, first choose the popular guy, 4 ways, right? 4 choose 1 way, and then that's it. And then he's connected to the remaining 3 people. How about this one? How many ways this one? This one's tricky. Which one? Oh, this one. Why one? Because here because this is a labeling problem. Once you identify 4 choose 2 ways, what are the endpoints? Who is the neighbor of 1? It's either a 3 or a 4. So there are 2 more choices there. So that's why. All right, so this one is, okay, is it 3 or 4? Half of the class says 3, half says 4. And some people say 1, it's not 1. Yes, it's 3 ways. You can, because it's a cycle, you can first fix one of them. Suppose that 1 is fixed. Then we need to choose the 2 neighbors of 1, and then the guy which is my friend's friend, right? So 3 choose 2 ways to choose these 2 guys, and then we already know the other guy who he will be. So 3 ways this one. That sucks. Okay, next one, this one. How many ways? Look for the special vertices. That's the key idea. This one was hard because there's no special vertex. All of them are kind of symmetric. Yeah, symmetry is in general, yeah, takes time to understand. Yes. The answer is 12. There are multiple ways you can decide how to do it. So one way would be the following. First, choose the special one. Which one is the special vertex here? Which of the vertices, 4 vertices, which one is the special guy? 1, 2, 3, 4. The shape technically looks like this, by the way. This is the same shape, right? I don't know. It feels to me that the shape, the vertex which is special is this one over here. This is the special. There are 4 ways I can choose that vertex. 4 choose 1. And then once I choose that, I can decide which one will be lonely in 3 ways. And boom. Or alternatively, we could have started with this. You might say, hey, no, this one seems special to me. Fine. 4 ways to choose this one. Then choose which one he's directly connected to. And then the other 2 are connected to that second guy. So this is first layer, second layer, third layer. All right. So this is 12. Next one. 5. How many ways? 6. All you do is decide which one will be eliminated. In total, there are 6 edges. Eliminate one of them. So in a sense, this case is extremely similar to this case over there. Do you guys see that? Those 2 cases are kind of duals of each other. Yeah, they are, because one of them has 1 edge, the other one had everything except 1. So they are kind of opposites of each other. And finally, this one is the same as having no edges. There's only one way to do this. Now, a lot of people would be asking, hey, Dr. Nal, how would you count this using, well, okay, so it all started with this idea, right? How many types of graphs? How many did we come up with? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 types of graphs. The question is, how would we have counted this using Burnside? Okay, so Burnside would have given us 11 as well. Okay, so this is a relatively harder thing to consider, but let me quickly tell you how it comes. So in total, there are 24 symmetries. Total is 64, of course. 2 to the power, what? 2 to the power 6. Why 2 to the power 6? Why is the total 64? Each graph has, so suppose that you have those, those 4 vertices. For 1, for instance, you need to choose whether he will be connected to 2 or not. You need to choose whether it's connected to 3 or not. You need to choose if there's an edge between 1 and 4. Decide whether there's an edge between 2 and 4. Decide whether there's an edge between 2 and 3. Decide whether there's Okay, so you know what I'm saying. So therefore 2 to the 6. Yes, the total number of labelings should be 2 to the 6. Perfect. Okay, I was saying the Burnside, right? So I almost lost my chain of thought there. All right, so oh shoot. Okay, well, okay. So this one is let me give you the idea. Ah, okay. So somehow I'm not able to delete that. Okay. Oh, there you go. My machine is stuck. All right. Oh, why are there 24 symmetries? What are those symmetries? So what I have in mind is the following. The symmetries is the swaps between vertices, and then the shape is the graph shape itself. All right. So do you guys see that? The 24 symmetries in this shape would be the number of ways we can permute the vertices, which there is 4 factorial ways, 24 ways. All right, so this one is a little bit harder. On AOPS, there's an article about it. You can read that article if you want. But for those of you, for the fun of it, so we counted here, there are 11 different type of graphs of size 4, right? How many graphs of size 5 and how many graphs of size 6, if you are wondering, and if you want to do it at home, if you enjoyed this so much, we're almost done, yes. I can tell you the numbers. The number of the 5 graphs is, let me tell you exactly, hold on, it should be here somewhere. Just give me a second. I think it was, I want to say 156, but I don't want to be wrong. Hold on, just give me a second. There is, come on. Okay, I don't know. Okay, I totally forgot. I think one of them is 156. Just give me a second. Hold on. Wait. Okay, I don't like college books. Usually I'm using college books for this, but college books have so much theory. I mean, there is, oh yeah, hold on. Was it 34? Oh yeah. This one is 34. This one is either 56 or 156. I forgot. Either 156 or 56. I totally forgot. Oh, you guys already have it? No, not 69. No. No. In total, there are, wait. Well, okay, I can't think of from the top of my head. Sorry for that. Yeah, I thought it was, well, yeah, okay, I might be wrong. Okay, sorry, guys. Okay, let me not speculate here. Oh, actually, hold on. I think I have it. Hold on. Just give me a second. Oh yeah. I have them. Yes. In total, 34 with 5, and then 156 with 6. Yes. And actually, I have the picture in front of me. I did it today. I was trying to figure out where I put it. Yes, I have it. It's such a nice exercise. So try to do it on your own. Try to create those 34 different graphs. And then if you have time, for instance, there are so many 6 graphs. You might wonder how many of the 6 graphs has say, for instance, 6 edges. Obviously, it can have at most how many edges? The 6 graph. The graph with 6 vertices can have at most 6 choose 2, which is 15 edges. Suppose that you have a graph with 6 edges. How many different graphs with 6 edges can you construct? And that's 21 of them. That's just a sub case of that 156. So one by one, you need to construct how many with 0 edges, how many with 1 edges, all the way up to how many with 15 edges. The case with 6 edges is 21, basically. Yeah, so this is a lot of stuff. Yeah, okay, I hope you guys enjoyed today. So we did cover a little bit of graphs, coloring problems, some of them without using Burnside, so most of them using Burnside, and then we also talked about symmetry. So it's a very nice topic, which is usually it kind of, oh, I forgot the polynomial question. All right, maybe next time I can show you that polynomial question as well. All right, so that's it. Thank you guys so much. Let me, well, I don't know if I can, yeah, this chat box is not working for me. Let me first stop the recording, so just in case I don't want to lose the video. So the video recording will be available on YouTube as well, so you guys can also check it there as well. Okay. All right, guys. See you.